Hrishi is a PhD student at the ARC-funded Centre for Information Resilience here at UQ, approaching his mid-candidature, I think, halfway through or thereabouts. And he's going to talk to us about EMIT, which I had hoped you had given me the acronym, but a deep learning framework for irregular clinical time series. Hrishi, over to you.
Thank you, Aaron, for the opportunity, and thank you, Dr. Scott, for the wonderful talk. So I'm going to present on EMIT. So let me just first tell you the name of EMIT. It's very mouthful. It's an event-based masking for irregular time series, but I won't refer to it. I just give it EMIT for now. Yeah. So where my talk fits in the perspective of Professor Scott's talk. So Professor Scott nicely summarized starting from data to model development to deployment. So I'm focusing more on the model development part itself, how we can handle the clinical time series data and create a useful deep learning model which can give good performance. So I'll start with the basics. So here is a snapshot of a clinical data. We have 4 variables: body temperature, blood oxygen, heart rate, and respiratory rate measured at every 15 minutes. And when we see this data sequentially measured over time, we call it a time series. And this perspective is powerful because if we see this data as a time series, we can then unlock a lot of different specialized tools, analytical tools developed for modeling this kind of time series data. So what's the benefit of modeling this kind of data? So one benefit, one application is mortality prediction. So where we try to predict, it's a very common benchmark in the AI deep learning based time series models, where we try to predict, given the 24 hours of patient's data, we predict whether the patient will survive or not after the 24 hours. And the other task is risk prediction, where we try to predict the disease like sepsis or some other phenotypes, where we take the data of patients for a few hours, and then our model will tell us whether our patient will develop sepsis after a few hours or not. So these are the two of the many applications. Others are like length of stay prediction, patient decomposition, and many others. But the problem is medical data are not often very tidy to work with. They are not like textbook time series, which I showed you here. There's a very simple time series, but medical data, they are often irregular. So let me tell you what it means by irregular. So this time series is a real time series I have picked up from the clinical data. Here we have 7 clinical variables measured for 48 hours. And each bar shows the measurement taken at that particular time point. So let's describe the challenges we can observe from the data. So first of all, we have inconsistent time interval where, for example, for the heart rate, initially we can see the bars are very close, like a dense, but as we move ahead with respect to time, the distance between the bars increases. It means the measurements are not taken at consistent intervals. And then we have some asynchronous observations. So for example, where we have heart rate and temperature, they are not sometimes aligned with respect to time. For example, heart rate might be measured at hour 1, but the temperature might be measured at 1 hour and 2 minutes. So they are not aligned with respect to time. That's also one of the challenge. And then we have sparsity in observations. So for example, heart rate, temperature, and the mean arterial pressure, they are measured very frequently. But if you look at the last 4 variables, the oxygen saturation, blood glucose, white blood cell, and platelet counts, they are very sparse. They are measured very few times compared to the other ones. So that also introduces challenge in modeling time series. And finally, we have limited label data. So this is a general challenge in the machine learning and deep learning domain. So by limited label data, I mean, what if we do not have enough sepsis patients in the first place to create a good model? So that's one of the challenge. And so traditionally, how people have handled these challenges, they try to replace the value. Like, for example, in oxygen saturation, we have a lot of missing values compared to heart rate, temperature, and MAP. So what people try to do is to replace the missing value with the mean value, or maybe they try to use the previously observed value as a valid value to replace it. But that's not a good idea because it introduces the noise in the data, artifacts in the data, which we do not want to model, because that value was not really observed. We are just replacing it with some meaningful observation, but that might not be actually relevant. So we can safely say that the traditional statistical models, they are not really equipped to handle this kind of irregular time series data, and hence we need something very specialized for this kind of data. And hence I pose my core question as how we can effectively model this kind of irregular sequential data with limited labels. And to address this question, we made two principal contributions. We designed this framework EMIT, which learns from the irregular data, and then we tested this EMIT model on the two popular clinical benchmarks, which I'll talk about in the experiments part. So here is a bit of detail about how we trained the EMIT to learn from irregular time series. It's a very simplified representation. If you are more interested to read about the actual details, I'll share the link of the paper at the end, but this is a very simplified view. So we are using something called pre-training and fine-tuning framework for this data. If I simply put this with an analogy, so let's say if someone wants to learn a language, we first teach them the basics of like grammar, sentence construction, etc. And then we teach the students how to write essay and all these things. So same thing we are doing here for the model. We are first teaching the model the structure of irregular time series itself. And for that, we first take the time series data and then we mask the values. By masking is more like we are removing that value and then telling the model to recreate, to find the missing, the masked value based on the other available values. So here we are forcing the model to use the unmasked values to identify what values we masked in the first place. And that's how our model learns the irregular nature of the data. So here we are not using any sepsis, any mortality prediction, any labels for this. We are just using the input itself. And once the model has mastered all the structure of irregular time series data, then we can fine-tune it for the specific task of interest. In this case, we used mortality prediction task. So for that, again, we take the patient vitals, then we feed it to model. Model will then predict whether patient will survive or not. And then we compare it with the ground truth, and based on the error difference, we'll train the model to improve. And after that, we'll get the final model that can help us predict the data which we did not use in the training. So now let me talk about the experiments. We used two popular clinical benchmarks dataset, which are MIMIC-3 and PhysioNet Challenge. So MIMIC-3 is electronic health records from US hospital, comprises more than 40,000 patients. And the PhysioNet Challenge, so PhysioNet is a website which hosts lots of physiological data, and it hosts also challenges every year. So in 2012, there was a challenge for mortality prediction, and we used that data for our EMIT to check the validity of EMIT. If you look at the statistics of the data, I want you to have attention at the average variable missing rate. We have about 90% missing values for the MIMIC-3 and about 80% for the PhysioNet, which indicates that data is highly irregular. And also about the percentage positive class. So about 10% in the data, about 10% cases were mortality and about 14% cases were mortality in PhysioNet. So I want to suggest a key takeaway from this is the data set is highly irregular, which represented true clinical data. So now let's see how our model EMIT performed with respect to the other state-of-the-art data set, the baselines. So we considered three different types of baselines. The first one is RNN based. I'm sorry, this is a bit of technical part, but I just want to say these were the state-of-the-art baselines. So we evaluated EMIT on three different metrics. The first one is ROC-AUC, which is the, in simple words, it's a discriminative ability of the EMIT to identify patients with mortality and patients without the mortality. And we can say that the EMIT outperformed with 89% accuracy. Our model EMIT outperformed the other baselines. So the last row represents the model. The second metric we used is the PR-AUC, which is the area under the curve of the precision and recall graph. So the ROC, the first metric, it doesn't really capture the imbalanced nature of the data set. So as I mentioned before, we have 10% mortality cases and 90% not mortality. But that's why the ROC accurately captures that part. We have about 89%, means, rounding off to like 90% cases mortality, 90% non-negative cases, 10% positive, which is really captured by the ROC. But the problem is the ROC AUC is not very detailed metric. We need to consider the false negatives, false positives effect of that while making the clinical decisions. And that's why we used PR AUC metric to evaluate that part. And we can again see the EMIT really beaten the other baselines in terms of the PR AUC as well. And then we also consider other metric where we wanted to keep a balance between recall and precision. So here we wanted to maximize the minimum value of recall and precision. So we want, ideally we want higher recall and precision, but in our EMIT we trained the model to keep the minimum bar at the highest point. So here we have like about 54.54 recall and precision, which is minimum. So if I simply explain, let's say I have 0.54 precision, then recall will be higher, at least equal or higher than the 0.54. So that's the metric we used. So to conclude, when we see the time series data as when we see electronic health records as time series data, it unlocks a lot of opportunities to model them with the latest statistical and AI models. But they pose challenges because the EHR is irregular in nature, so we need to handle them in a specialized way, and hence we created the model EMIT, which learns from these kind of complex time series data. We evaluated this model on the popular benchmarks on mortality prediction tasks, which clearly outperform the other baselines. And clinically, this model can help make reliable predictions for the task of interest like mortality or sepsis, with fewer false alarms, of course. So our future work focuses on making explainable models for the clinicians, because this model was very black box in nature. It just gives you a number like the risk score, whether the patient will survive or not, but they are not very informative in that way. What if we have a model that doctors can interpret, like why this model gave a specific score? What were the internal mechanisms? So I'm now focusing on that part. And also I'm working on creating a stronger something called foundation model, where we want to train the model from multiple data sets so that it can learn very rich patterns, which we can then use to fine tune with other tasks of interest like sepsis or length of stay. So it's just like we are training one single model which can work with any kind of data, any kind of task. So that's the foundation part. And thank you for your attention and talk. If you are more interested in reading the paper, please feel free to scan the barcode. Thank you.